Biomechanics of sit to stand transition. Sitting and standing, also known as STS, are two of the most common daily activities. Part of being so essential and common comes from the ease of the movement for a human being with no physical limitation. As time goes on, sitting and standing can start to become a difficult task, especially considering a person's age. To elderly adults, the ability to sit and stand without any help is a sign of independence and security. Research shows causal relationships between postures and conditions like back pain. Other causes like sleep deprivation, stress, and long-term physical inactivity or prolonged static unnatural postural stress could be significant co-founders for various health conditions related to sitting and standing. The ergonomics team at Cornell University identified that sitting for longer than 20 minutes has negative effects on the human body by increased problems in the musculoskeletal system, with some problems such as back and neck pain. It is recommended moving regularly. People should always try to stand or move every 20 to 30 minutes. The muscle movements are not the only aspects that need to be contemplated. A big part of the STS transfer is the way in which the person is positioned in the way they apply the force in the ground to maintain the balance. There are three factors taken in consideration for the analysis of the STS transition. The first factor is the kinematic analysis, where the position of the subjects and the linear and angular velocities are taken into consideration. The second is the kinetic evaluation, which are the torque forces of the articulations. At last, we have the comparison of the results between both subjects. The STS transition consists in four phases. Phase 1, weight shift. Phase 2, transition. Phase 3, lift. And Phase 4, stabilization. The muscles involved in the STS are erector spine, rectus femoris, and vastus medialis during the first phase, and bicep femoris, gluteus maximus, and rectus abdominis during the second phase. In 1962, Schobert defined three different sitting postures based on the location of center of gravity of the body and the proportion of body weight transmitted to the floor by the feet. Schobert termed these three sitting postures as anterior, medial, and posterior. These three postures also differ concerning the shape of the lumbar spine. He showed radiographically that his subjects posteriorly rotated their pelvises 40 degrees on average during the transition of standing to sit. During the sitting position, the upper body weight is carried essentially by the ischial tuberosities. Elevated pressure on the ischial tuberosities are closely associated with elevated spinal loads. A lordotic lumbar spine has been considered a load absorber in the manner of spring, and it was found that the lumbar lordosis reduces intradiscal pressures and transferring the load to the posterior annulus and apophyseal joints. These findings suggested that a lordosis in the lumbar spine may have a protective effect on the lower back problems. Coburn used electromyography to demonstrate that the support of the lumbar spine in seated posture is sufficient to rest the back muscles. This project has the purpose of analyze and compare the sitting position of two subjects of different ages. This to see the difference of techniques comparing the velocity of the hip, knee, and ankle in linear and angular movements between subjects. This to have a clear idea of the angle of attack from the three parts of the leg and the force transfer from the movement. Two female volunteers of different ages were selected for this study. We analyzed the movement from a sagittal plane, assuming the symmetry of the body. Using a camera, we recorded the movement of the subject standing up from a chair without the help of the hands. We used the beacon making system to keep track of the movement of the joints in the video. We used black tape to mark the toe, ankle, knee, hip, shoulder, elbow, and wrist. Once the video was recorded, we processed and analyzed the biomechanical movement using skill spector tracking software. With the help of the software, we were able to obtain the position of the joints, angles, and the linear and angular velocities of the joints. Using Excel, we copied the data from the graphs obtained in Skill Spector and pasted on an Excel sheet to obtain the equations for each kinematic value by plotting the position, angular, and linear velocity values and obtaining the trend line of the graph. Then we calculated the moments of the knee and hip joints of each subject for comparison. We use a free body diagram to calculate the torques in the 4 phases of the movement. We obtained the hip angle and position graphs and their specific equations. Also, the hip velocity and hip angular velocity and their specific equations. Comparing the velocity in the 3 phases, we can observe that the youngest has faster movements in both axes, being 1.64 meters per second in the x-axis and 1.06 meters per second in the y-axis. Also, during the second phase, we can observe that the mature subject closes her hip joint more than the younger by 7.81 degrees, and in phase 3, the difference of angle is 29.83 degrees. The younger subject has a more straightened up posture by 5.67 degrees. In the mature adult knee angle graph, we can observe a little peak between phase 1 and phase 2. This is due that the mature subject swings her feet a little to the back to create momentum to start the movement. In the first phase, the younger subject shows almost a right angle on her knee joint, while the mature subject's joint angle is more closed. During the second phase, the mature subject has a more closed angle by 14.73 degrees. On the next phase, the younger subject has a more open angle by 25.04 degrees than the other subject. On the final phase, the younger subject has more straightened up knee joint angle. The difference between both subjects is 15.96 degrees. On the young adult graph, we can observe how the ankle's position changes a little. This is because that's the moment as she gets down off the chair. On the other part, we can see that the mature subject's ankle position changes quickly, then stabilizes on the ground. This is because, as we mentioned before, the subject swings her feet before starting the movement. We calculated the weight and measures of the trunk and thighs of the subject to analyze the torque created during each phase. In the hip torque graph, we can observe that the torques created on the hip in phase 1, 2, and 3 are of bigger magnitude on the mature subject than the younger subject. The torque created on the final phase is bigger on the younger than on the more mature subject. On the other hand, on the knee torque graph, we can say that the mature subject has only a bigger initial torque than the younger subject. On the remaining phases, the younger subject has a bigger and more constant torque than the mature one. As a conclusion for this project, we can say that the kinematic analysis allowed us to evaluate the differences in STS transition between the young adult and the mature adult. As for the kinetic analysis, it helped us to confirm the results in the kinematic analysis by explaining the STS transition differences between our subjects. Particularly, young adults do less use of their hands and feet to help them to stand, while mature adults start to increase the use of their limbs to support the upper body weight and to keep balance to stand. This project allowed us to understand the changing of the biomechanical function of a person through time, as interpreting the obtained data to understand the mechanisms of STS transition. At watching the videos, we could observe the phases of the movements, and with the help of tracking softwares, we were able to model the biomechanics of said movements to analyze with the help of physics. The model of the STS transition has many applications in biomedical engineering, like development of prosthetics, skeletons, rehabilitation, among others.